Welcome to The Explainer. Today, we are diving headfirst into the incredibly high-stakes world of quantum computing. We're looking at a brand new and, honestly, highly controversial timeline that Microsoft just dropped. They've made a monumental announcement about the future of computing, and let me tell you, it's absolutely sending shockwaves through the entire physics community.
So let's get right into this incredibly bold claim. Microsoft has officially announced plans to build a useful, fully functioning quantum computer in just 3 years. Now, this is a massive deal because it literally cuts their previous timeline completely in half. They're effectively hitting the fast-forward button on a technological race that, frankly, a lot of scientists believe is still decades away from the finish line.
And you can really see the sheer corporate ambition at play here. This quote comes straight from Chetan Nayak, the physicist leading Microsoft's quantum computing effort. Moving a target for a scalable quantum machine from 2033 all the way to 2029, that is a breathtaking acceleration. But, it really begs the question, how exactly do they plan to pull this off, and why are so many experts completely unconvinced?
To truly grasp the science and the drama here, we're going to follow this roadmap. First, Microsoft's bold quantum claim. Then, unpacking topological qubits. After that, we'll look at the scientific pushback. And finally, a quantum deadline.
All right, Part 1. Microsoft's bold quantum claim and how they're accelerating the timeline to a practical machine.
So this entire push to the 2029 deadline relies heavily on improvements made to one specific piece of tech. It's called the Majorana 2 chip. Now, this is a microscopic device, and it's every bit as controversial as its predecessor was about 18 months ago. Microsoft is claiming that this chip holds the exact building blocks needed to scale up rapidly. But on the flip side, critics are arguing that there is a serious lack of hard evidence showing the device actually works the way they say it does.
Moving right along to Part 2, unpacking topological qubits. Basically, how Microsoft plans to build a better brain.
Now, as a quick refresher, conventional computers process one solution at a time using bits. But a quantum computer manipulates qubits, which can actually exist in superpositions of 0 and 1 simultaneously. Because of these superposition states, a quantum computer can analyze just vast amounts of inputs all at once. The wave-like quantum states actually interfere with one another, kind of canceling out the wrong solutions so the correct one just naturally pops out. It's built to solve problems that would completely crash a standard supercomputer.
But here's the catch, and it's a big one. These delicate quantum states suffer from something called decoherence. Basically, they fuzz out super quickly the moment they're exposed to environmental noise. That is exactly why today's quantum computers max out at just a few hundred qubits. Because standard qubits are so fragile, Microsoft is betting absolutely everything on a highly complex design known as a topological qubit. The idea is that its unusual shape theoretically protects it from the environment, shielding that delicate calculation from destructive noise.
So how on earth do you actually build one of these things? Well, Microsoft uses this incredible microscopic engineering process. First, they take a microchip made of semiconducting layers and lay down a tiny strip of superconducting metal. This creates a sort of wire-like region of superconductivity. Next, the electrons pair up inside this region. And finally, a tiny electron, called a quantum dot, injects one additional unpaired electron. According to Microsoft, you end up with a wire that has either an even or an odd number of electrons. The even state is R0, and the odd state with that one lone electron is R1.
And here's where it gets really mind-bending. The crucial part is what happens to that single lone electron. In theory, quantum effects create what physicists call Majorana zero modes. This means that lone electron becomes completely delocalized. It literally exists at every single location along that wire all at once. Because the electron is spread out like this, it makes it incredibly difficult for outside noise to disturb it. It's like a built-in shield protecting the complex math happening inside.
Which brings us to Part 3, the scientific pushback and why so many physicists are highly skeptical.
To be fair, Microsoft freely acknowledges they've been pretty cagey with their peers in the past. Chetan Nayak actually admitted their old stance was basically, hey, just trust us. But he says they're turning a new page, revealing more of their methods, and claiming they now have unpublished data, proving they can fully control these qubits and even run algorithms.
But you see, that whole trust us history, it heavily rankles independent scientists. Physicists like Sergei Frolov from the University of Pittsburgh strongly push back against Microsoft's narrative. Frolov points out what he calls a sustained pattern of unreliable claims, noting that these delocalized states have been reported and retracted over the years, causing a lot of controversy. He argues that to hit a 2029 target, you'd need a working prototype right this second. And looking at the published results, he calls that scenario highly implausible.
And the scientific pushback here isn't just general doubt, it is highly specific and data-driven. Critics like Henry Legg and Frolov explain that achieving these Majorana states takes extreme precision. Legg argues that Microsoft's data might actually just be showing the system settling into a quiet spot within a whole landscape of noise. Plus, they point out that the switching behavior Microsoft is seeing might have a much simpler explanation, like an electron just hopping on and off an ordinary incidentally formed quantum dot. Above all, the skeptics emphasize that there is zero published proof that the device actually works as a controllable qubit, and that the impressive endurance times don't automatically mean a quantum superposition is actually surviving.
All right, let's wrap up with part 4, a quantum deadline and this incredible race to 2029.
So Microsoft is moving aggressively fast. Back in February 2025, they were getting states that lasted about 2 milliseconds using superconducting aluminum. But today, they report that by swapping out aluminum for lead, they boosted the binding strength and shot that endurance time up from milliseconds to an astonishing 20 seconds. Nayak claims this 20-second threshold is exactly what they need to put a full-fledged quantum computer within reach, and that's what's driving this aggressive sprint to 2029.
But as that deadline shrinks, the skepticism is definitely getting louder. Critics, like Henry Legg, maintain that Microsoft is looking at their data and just interpreting it to fit the conclusion they already want. He suggests the researchers are convincing themselves of things the actual published data just doesn't support, moving away from hard science and into what he frankly calls a quasi-religion.
So what should you take away from all this? Microsoft has set a remarkably tight schedule, cutting their development time completely in half, based on breakthroughs that the broader scientific community is still fiercely debating. The stakes literally could not be higher. Will Microsoft prove the skeptics wrong and deliver a historic technological revolution in just 3 years? Or are they rushing headfirst toward a devastating scientific judgment day? I'm going to leave you with that provocative thought. Thanks so much for joining me for this explainer, and definitely keep your eyes on 2029.